In this video, we are going to take our knowledge of partial fractions and finally apply it to series. Now, we have done some previous videos where we looked at entering in this series into Mathematica and creating a table of both the a of n and the s sub n values. And from that table, we were able to see a pattern going on with the partial sums of this series. But it was not at all clear from that table why we should get such a nice formula for the sum of this series. And partial fractions can help shed some light to that mystery. So an example that we asked to do previously was to take 1 over n times n plus 1 and rewrite it in its partial fractions decomposition. When you do that, you find that the a value that goes in the numerator of the a over n term is 1, and the b value, serving as the numerator in the b over n plus 1 term, becomes negative 1. And so we can substitute in this rational function for this difference of more simple rational functions. If we now write out the first handful of terms in this series, plugging in n is equal to 1, we get 1 over 1 minus 1 over 2 to represent the first term in this sum. We then add to that what happens when we plug in n is equal to 2, 1 over 2 minus 1 over 3, and add to that what happens when we plug in n is 3, 4, and so on. And we write all these things out. And what's brilliant about this decomposition is we can see a beautiful cancellation of terms. Here, I subtract 1/2 in the first term, coming from this 1 over n plus 1 with this minus sign here when n is equal to 1. However, in the very next term, when n is equal to 2, I get a 1/2 in the first part of this decomposition. And so all I've done is subtracted 1/2 in the first term and then added it back again in the second term. So this negative 1/2 and this 1/2 cancel. Similarly, I subtract a 1/3 in the second term, only to add it back as the first addend in my third term. So this negative 1/3 and this 1/3 cancel. And we continue in this way, where the only things that do not cancel when we stop at a particular partial sum are the first term and the last term. Altogether, what this allows us to do is come up with an explicit formula for s sub n, namely 1 for the 1 over 1 minus the last remaining term, 1 over n plus 1. And when we take the limit of that sequence of partial sums, we find that the limit is 1. So although it may not have been obvious to us why we were getting such a nice pattern when we plugged these into the computer, when we use partial fractions to get this decomposition, we can see precisely what is happening and why we're getting this particular formula. Now I'd like to walk through one more example of a telescoping series through partial fractions. So my example of this series is now 4 over 4n minus 3 times 4n plus 1. Let's first use partial fractions to take this elaborate rational function and see if we can write it as a sum of a over 4n minus 3 and b over 4n plus 1. In other words, take the more complicated rational function and write it as a sum of simpler rational functions. Now the first step in this process is to replace these nice simple fractions with equivalent fractions that have a common denominator in order for us to be able to add across the numerators and leave the common denominator there. So as you can see, I've replaced a over 4n minus 3 with this expression right here, a times the quantity 4n plus 1 over this denominator, quantity 4n minus 3 times quantity 4n plus 1. And I've done something similar with b. We now have this common denominator and add across the numerators to get this expression right here, and all of that is equal to our original rational function. Our next step is to clear denominators to eliminate fractions from this messy equation altogether, and multiplying both sides of this equation by 4n minus 3 times 4n plus 1 yields just an equation of the numerators. 4 is equal to a times the quantity 4n plus 1 plus b times the quantity 4n minus 3. Now the next step in our process was to distribute the a's and the b's to each of these terms and regroup our like terms to obtain this equation right here. And really, moving forward for the next step, I like to think of this as having colors, and I like to think of this equation more along the lines of this equation right here, where over on the left, I'm going to add in a secret 0 times n term, and I'm going to color the coefficients on the n's equally, and I'm going to color the constant terms equally. For me, the purpose of the coloring scheme is to show me the two equations that we're going to have with our two unknowns, a and b, and how we're going to eliminate n from this expression altogether. And the way that we're going to do that is to set the colored parts equal to one another. 0 is equal to 4 times the quantity a plus b, and 4 is equal to a minus 3b. At this point, all we need to do is use some of our familiar techniques from algebra to solve for the variables in question, a and b. One way to do this is to focus first on the green equation, noting that dividing both sides by 4 and then moving the a to the other side, we get that b is equal to negative a. If I then make that substitution for b into the blue equation, I find that 4 is equal to 4a, and therefore a is equal to 1. Then plugging that value of a back into this equation, I find that b is equal to negative 1, and those a's and b's that I introduced in the beginning are not a mystery any longer. We have values for them now, namely 1 and negative 1. Last but not least, let's go back to our original series and see how this partial fractions decomposition helps us. In particular, when I split up my original rational function in this particular way and write out the first few terms in expanded form, I find the same pattern happening. In the first term, I subtract a 1/5, and in the second term, I add it. So these terms right here cancel. Similarly, in the second term, I subtract a 1/9, only to add it back in again in the third term. So these terms cancel. That pattern repeats until I obtain a formula for the nth partial sum of this series as 1 minus 1 over the quantity 4n plus 1. And again, taking limits as n approaches infinity, I'm able to find the limit of this partial sum. Now I'd like to end this set of slides by saying that both of my examples had a partial sum of the number 1, and both of my examples had a 1 and a negative 1 in the numerators right here. It's not always the case that a telescoping series has a sum of 1, but what a telescoping series is more generally is a finite series disguised as an infinite series. And you can see that this is a finite series by all the cancellation that I have going on. So although these values can be different constants here, different first terms, maybe it's not just the first term that's left. Maybe the first handful of terms stick around. There are variations on the types of behavior that we can see with telescoping series, but those are slightly more advanced problems, and so we want to master these basics first.